microchannel. We can see that this is the single phase inlet, this is the side channel, both meet at the 90-degree junction, which makes it a T-junction, and here is the main channel through which the slug flow will occur. From here the air comes, from here the water comes, both interact with each other at the T-junction. Here air causes viscous shear plus the pressure drop. Both factors, pressure drop and viscous shear, leads to the generation of water slugs in continuous air. If we apply the constant wall heat flux, we will study the heat transfer enhancement for the case of slug flow in comparison to the single phase flows. We have applied heat flux only in this section and not in this section. The reason is that we wanted the velocity boundary layer to be fully developed before the thermal boundary layer comes into play. So in this section, so here the velocity boundary layer is fully developed and only the thermal boundary layer is developing. The heat flux is of some electronic device which is we are going to be cooled. So if we reverse the case, we take the water to the here and air replaces water at its place. We can see that we will have continuous water phase and the air bubbles dispersed in that continuous water phase. We will compare both these cases of continuous air in which water slugs are dispersed and the continuous water in which air bubbles are dispersed with the single phase air and single phase water, to know which case performs better for the heat transfer enhancement as a result of this comparative analysis. So actually in our thesis we had two sections. First of all, we did not apply heat flux, we just carried out machine dependent study, we carried out validation of numerical model, and then we studied the hydrodynamic analysis without introducing any heat transfer aspect. After having done this, we proceeded with applying the constant wall heat flux to study the heat transfer enhancement for the use of microcooling of electronics. How do we do this in NCS fluent? We will see here. First of all, we have opened the workbench, and from here we drag the fluid flow fluent here. Then we right click on the geometry, and here we will click on the new design modular geometry. The design modular geometry is opening. So this is the geometry of the T-junction microchannel which we will create in the design modeler. Design modeler is actually starting, so it will take a time. So the design modeler has opened. Now we will see how we create our geometry. Click on this, bring it in the XY plane, then we click and look at face section. We fit the screen to zoom the screen to fit screen fit. Then we set the units to millimeter because all our dimensions in millimeter. So now we are going to make the sketch of a T-junction. From here we draw a line here. This horizontal line, again a vertical line. In this way we will create the geometry of the microchannel with T-junction. Similar pattern will be followed here as we had followed in the upper layer. So now we will go to the constraints, and in the constraints we will click on the equal length constraint, because there is a great symmetry between in our geometry. So we will make sure that all lengths are equal, so we don't need to add dimensions again and again. We will just put one dimension and it will make sure that all other its counterparts are equal. Now we are ready to go to the dimension section. The dimension section, we click on the general, and from here we click on this line. This is the length of the side of the single phase inlet. This is 19.2 millimeter, and we click here, which is basically the width of the side channel, and that is 0.8 mm. Then we click here H3, the unheated section that we had seen earlier, and this is the section upon which we will apply the heat flux, and this is the 55 mm. Click here to bring the screen more viable to read. Here click, we add the width of the main channel, and that is also 0.8 mm, and the final dimension is of the height of the side channel, and this is 24.5 mm. Again click here to zoom to fit. So now we have all the dimensions. Here is the single phase inlet length. Here is the length of the width of the of the side channel. Here is the length of the unheated section, length of the heated section, width of the main channel, and this is the length of the side channel. So all the dimensions have been done. So we click on the generate button to generate the geometry. Geometry has been generated. Now we have to create a surface from this. So we go to the concept button, click here, and then we click on the surfaces from sketches. We select the sketch 1, apply, click on the apply, and then we click on the generate. So here we can see that this is our sketch and this is our surface body. So our microchannel has been generated. We click on the generate, and then we close it. Our geometry has been created successfully. After having done with the geometry, we will go to the mesh section, but before that we actually save the project so that we may not lose it during the process. So we will save it on some destination. After saving the file, we now click on the right click on the mesh to open the mesh to do the meshing of our geometry. Click on the edit. The meshing will start. It will take a time. We will wait for it to be opened. So the mesh has opened. We click in here to bring it to XY plane. We check the units. Units are meter kg. We convert them to millimeter kg. So we have successfully changed the units. Now we come here to click on the mesh. By right clicking on the mesh, a dialog box appears. In the insert button there are further options. We click on the phase meshing. We click on the sizing. In the sizing we click on the phase. Make sure from here that you have selected the phase selection. So we have selected the phase. I click here, click on the apply. So we can see clearly what is happening here. Then we put the element size of 0.1, which we have selected after a thorough mesh independence study. Then this behavior is okay. We set the default size is okay. All other things are okay. So then we come here, and then we see that the size function is uniform. We change it to proximity and curvature. This will help us in convergence, in dealing with the convergence related issues. This actually makes the mesh more accurate and more resistant to instability. And then we introduce inflation. So what is the purpose of inflation? Inflation is being added so that we can capture the boundary phenomenon, the phenomenon that is occurring at the boundary. What does inflation do? It makes the mesh very refined along the boundaries, while coarse at the center, so that the boundary layer that is being generated at the boundaries is successfully and completely captured. So we select the maximum layers of the inflation. It is 11, and the growth rate of 2. Then we click on the mesh. In the mesh, here we select the inflation of 1, overall growth rate is of 1, and then we right click and then we generate the mesh. So it will take a while for mesh to be generated successfully. We wait for this to be generated. You can see that it is now doing the meshing of the faces of the surface body. So now it is calculating the cross field. It will take a while for it to be completed. So we recap while it is doing this. We have done first of all face sizing with the max size of 0.1 mm, and then we have added inflation with the maximum layers of 11, growth rate of 2. Inflation is done to capture the phenomenon that is occurring at the boundary. Inflation, what does inflation do? It makes the boundary, it makes the mesh very defined near along the boundaries, while it gradually becomes coarser and coarser as we move towards from boundaries to the center of the geometry. So it will take a while. So we can see that mesh has been generated as all the cells are nearly cubic. So a symmetric mesh has been generated, but we can see that no inflation has been added. This is because in the inflation section we had not selected the boundaries upon which we wanted to apply the inflation. So here in the boundaries we select the boundaries. We will select all boundaries except the inlets and outlets. And then we click on the apply. We have 9 edges on which it will apply the inflation. So we will again click on the generate mesh. So the whole procedure will be repeated again, but it will take lesser time than the earlier one. So we will have to wait again for a while for mesh to be completed and generated. So the mesh has been completed. Now we look at it, how the mesh looks. So we can see that the inflation has been added. The inflation has caused some skewness in the cells, but still we have good quality of the mesh. We can check the quality of the mesh from here, the statistics section. Okay, in the statistics section we have this. We will actually check the quality from here. Here is separate section for the quality. In the 19th variant or the 17th variant, this used to be in the statistics section, but here in the 18th variant we have the quality in the separate section of its own. So we select the mesh metric to be, for example, to be skewness, which is considered the main parameter, and we can see that the maximum skewness is 0.5. so this is acceptable. Skewness should be less than 0.8, so this is acceptable. Now we go to the naming of the sections. We click on the edge selection, and then we click here, press N, and it comes to be air inlet. Then we click here and it is water inlet. Then we click here and press N, and it becomes the outlet. And now we have to, what we have to do, we have to define the boundaries, wall boundaries. So here it is. Here, this is the section that we can call cold walls, because these are the walls on which we won't apply the heat flux, because and these are the walls upon which we will apply the heat flux. We will say them to be hot walls. And then we can see that the name selection is air inlet, water inlet, pressure outlet, cold walls, and the hot walls. So now we are good to go. We will, before closing the mesh, we will right click on the mesh and update it. So it's says that it has successfully translated to the fluent. We now will close it. After done with the meshing, we will go to the setup section, which is the simulation settings section, in which we will set the simulation settings and simulation parameters. We right click on the setup, click on edit. Fluent will start to be opened. It is starting. It will take a while. Here dialog box open. We click on the double precision for more accuracy in the results. We click on the parallel and we select the processes to be 4, and then we click on the OK. You can consider them to be series, but I will click on the parallel. It will do the job in a more rapid way. Click on the OK. It will take a time, so we will wait for this to be opened. It is actually opening, but it will take some time. So here it is now opening. We can see that it to be opening. So the meshed geometry is being loaded into the setup section. We would have to wait for a while. It is actually loading the whole setup. It is actually loading the geometry, the meshing, all the face selections and all other parameters, all the faces, all the nodes. Just a few minutes more and we will be ready to go. So now it has successfully loaded the whole setup. We can see that here is the T-junction with the meshing being done. So now we come to the simulation settings. The solver will be pressure based. Velocity formation will be absolute. The geometry is planar. We can see that this is planar geometry, and the time solution will be transient. We will actually consider the slug formation and then the heat removal by the slug. This is transition, and in the model, because we have two phases, air and water, which are two immiscible phases, this is a multi-phase problem. So we will select the volume of fluid multi-phase model, because our main concern here is the interface tracking, which is recommended for the slug flows. Volume of fluid is recommended, so we will be going with it. There are number of 2 L phases: volume of fluid, explicit formation, volume fraction cutoff, column number is 0.25, and this has been checked implicit body force to ensure the stability of the solution. Click on the OK. Here you can see that for the VOF with explicit, the discretization scheme will be for pressure will be presto, and for volume fraction to geo reconstruct. Okay, after selecting the volume of fluid model, we go to the material section. In the material section, we define the material which we are going to use in our simulation. We can see that air is already available here. So we will just change the properties which we have in the research paper. Okay, so we will vary these properties. And then we click on the fluent database. From here we will select the water, because one fluid is air and the second fluid is the water. Here we go to the water liquid, we copy it and then we close it, and then we close it too. Here now we have selected two materials. Now we come here. One more thing that I forgot, sorry for that. We have to on the energy equation, because we are going to apply the heat flux on the boundaries, wall boundaries. So we have clicked on the energy equation and it has been turned on. So now we are able to take into account the temperature effects. So in the multi-phase, in the model section, the multi-phase section, the phase section, we have two phases. Phase 1 is the primary phase. We name it to be air. Okay. And in the secondary phase, which is phase 2, we double click on this, dialog box opens. We name it to be water, because in this case, in this scenario, in this case study, we have the air as the continuous and as the primary and the water liquid as the secondary or the dispersed phase. Then we go to the phase interaction box. We double click on this, a dialog box will open. In this we will go to the surface tension, and in the surface tension we come to the surface tension force modeling. We check the box name titled wall adhesion, and then here we consider the surface tension to be 0.07288, which is mentioned in the literature for the case of water and air. We have checked the wall adhesion to introduce the contact angle at the walls. By playing with the contact angle, we can vary the superhydrophobicity of the walls, which I had discussed earlier, that we will discuss in the setup section. So we will have turned it on when the contact angle is much greater than 90 degree. We can say that we have hydrophobicity. So we will see that we will consider the contact angle for this scenario to be 161, which makes the walls to be highly superphobic. Click on the OK. Then we come here at the fluids. We can see that we have considered here the properties to be constant, which will be okay, which will be correct if the temperature variations are very small. But if the temperature variations are large, we can incorporate other methods for the property introduction. For example, we can consider piecewise linear, piecewise polynomial, or the polynomial as a function of temperature. So just for the sake of tutorial, just for the sake of introduction to my MS thesis, I have considered the properties to be constant, but otherwise in this case the temperatures are going to be vary in a very large amount. So we will be going with either with the piecewise linear or piecewise polynomial. So in this way the density as a function of temperature will be introduced and all the coefficients will be entered here. But for the sake of simplicity, for the sake of tutorial, I will be going with the constant properties. So I'll return it to the constant. All the properties can be put as a function of temperature in case the temperature variations are large and you know that the properties are going to change with the temperature. So in that case the constant properties will not be valid option, and you need to incorporate the properties as a function of temperature in terms of either piecewise linear, piecewise polynomial, or polynomial. For the sake of simplicity, I am just going with the constant properties. But in actual the properties will vary because the temperatures are going to vary by very much amount. So similar cases for the water, we can again change the properties here as a function of temperature in case temperature variations are large and we know that the properties are going to vary. Then we come to the boundaries condition section. We double click on the air inlet. Dialog box will appear soon. So here it is. We enter the velocity magnitude to be which we have in literature. Then we come to it is the 293. The inlet temperature, the whole geometry is at room temperature 20 degrees Celsius. So we consider it to be 293 Kelvin. This is the velocity inlet for the air inlet. I am mentioning the velocity. You can change it to be any kind because I had the velocity in literature research paper, so I am going with the velocity inlet, mentioning velocity here, and here in the thermal section I am mentioning the temperature. at which the air is entering the channel. Then we come to the air because it is primary phase, so there would nothing for us to play with, while in the case of water we would have the option to vary the volume fraction. But in the air inlet we know that pure air is coming, there is no water, so we'll put the water fraction in the air inlet to be 0. So it means that pure air, 100% air is coming from the air inlet. And then we come to the water inlet boundary condition. It is open, it will take a while. So here we enter, this is again velocity inlet boundary condition for the water inlet, because I know the velocity here and I put the velocity that is of water at inlet, water inlet. Again it is entering the microchannel at temperature of 293, so I will consider it okay. Then again we come to the water section, because air is the primary phase, its volume fraction cannot be played with, while water is the secondary phase, so we will change its volume fraction. Here we know that pure water is coming, there is no air, so we will put the volume fraction to be 1. It means that air is 0 in the water inlet and only 100% water is coming from the water inlet. Then we come to the cold valves to specify the valve boundary conditions. So here, first of all, we set the contact angle. I had mentioned that by playing with the contact angle we can play with the hydrophobicity. I have mentioned the contact angle 161, which is very larger than 90 degrees, which makes the valve very highly super hydrophobic. I have mentioned this value because it is mentioned in the literature in my research paper that I am following. So it is cold valve, no heat flux will be applied. Valve thickness is 0.0025, and we consider the material to be aluminum, or we can vary it by selecting it in the material section. In the material section, just as we had selected the fluids, we will double click on the solids, on the aluminum, and from here we can go to the fluid database, we change it to solid, and from here we select the steel. So here we have the steel now in our material selection. And then when we come to the cold valves, we change it to material to steel. So heat flux is 0 because no heat flux is being applied at the cold valves. So valve thickness is 0.0025 meter and the contact angle is 161. In the hot valve section, in the hot valves, we will see the only difference would be the value of the heat flux. In the cold valves, we had mentioned the contact angle 161, here it is again the 161. Heat flux here would be 8850. Okay, and the valve thickness will again be 10025, and it is with the steel material name. So the difference between hot valve and cold valve is that in the cold valve section we had mentioned here 0, meaning no heat flux is applied, while in the hot valve we have mentioned the value of some value of the heat flux, meaning that heat flux is being applied at the valves. All other things are the same. Click on the OK. Then we come to the method, solution methods. In the solution methods, we will mention the different discretization schemes, different interface tracking schemes, will specify them. For pressure velocity coupling, we go with the piezo because it is more stable, it is more convenient to go with. And then we will have to wait a while, it is taking time. For special discretization, we consider it to be green gauze cell based. We know that for the explicit volume of fluid multiphase model, the pressure discretization scheme will be Presto. We have selected them for momentum second order upwind, which is good, and the volume fraction will be done by geo construct scheme, and the energy is also being discretized by second order upwind, which is good, which is more accurate. But the transient formulation cannot be converted to second order because it is the explicit VOF. If we consider to second order, it will again switch it to the first order, saying that second order implicit transient formulation is not compatible with the explicit VOF. So it is again, we can see that it is again first order implicit, so it is good. Now we come to the here the monitors. In the monitors we go to the residue files, report files, and we consider new. So basically the monitors are added at the surface to study the variation of different parameters as the simulation goes on. We firstly select on the click on the new, right click, and from there surface report we click on the area weighted average. So we will firstly consider the area weighted. We will want to know the slug movement, at which point the slug is moving. So we will consider the volume fraction, the field variable to be phases, volume fraction, and of the water, because water slug will be dispersed in the continuous air, and at which point it will be moving. We will draw a line that whenever a water slug will be moving through this line, it will let us know that that the slug has passed through this line. So we will know that now a slug has emerged and is passing through our geometry. So in this way we can count the number of slugs, we can count the time that a slug is taking to move in the slug, and we can play with this data, and we can extract various other parameters by using this data. So we can put this points to be 0.06, so that to make sure that the slug has fully generated. This is basically the width of the microchannel, which is know that 0.8 millimeter or 0.008 meter. We create a new line. This line has been created. This is the line 6. We select these all. We name it to be VF, volume fraction of the water of the slug. So now we can see the area weighted average report of the volume fraction of the water slug at the line 6 we are going to monitor. Here is the VF, volume fraction, with the time. This is the thing that we are going to monitor. Change the name so that it is convenient for us to identify in case of multiple reports. Into console. So into console means when the simulation will be running, it will be constantly updating and displaying it on the screen for our convenience. We click on the OK. Report has been generated. So now we will again click here, right click on the new. From here on clicking on the new, we have the area weighted average again, but this time not for the phase fraction but for the temperature, because we also want to see the variation of the wall temperature. So we will select from here the wall temperature, and we will select the hot walls, because we are applying the heat flux only on the hot walls. So we will be able to consider the variation of wall temperature only along the hot walls. So we selected the hot walls. Again same things that we had done in for the case of volume fraction. Here we name it to be TW, meaning wall temperature. This is the report of, this is a monitor of area weighted average of wall temperature along the hot walls that we are going to monitor. Click on the OK, name it to be TW, and change the name here as well, and then we have this. So another report has been generated, TW name. Then we come to the calculation activities. The calculation activities this is basically autosave, that after how much time steps you want the simulation to be saved, so that in case of electricity breakdown or any shutdown or any other issue, your whole simulation does not get ruined or does not get lost. To save your data from being lost, we auto save the simulation after some time steps. So I usually mention 2500. This is a reasonable. In case of very small number of time steps, the size of the data becomes larger, because more and more files will be saved, and in case of very large time steps, you have the probability of data being lost in case of any breakdown. So this is a reasonable value, 2500. You can select any other value which you deem more suitable for your case. And then we will consider here, click on the create to create the CDAT files, which will be helpful for our CFD post processing. I click on the all variables, because any variable can be handy while we'll be doing the post processing. So after doing this, we click on the OK. Here it is writing ff.cst, meaning that it is writing a post processing file. Then we come to the initialization. In the initialization, we click on the all standard. In initialization, in the all zones, we set the volume fraction to be 0, meaning that no water is present in the microchannel at the time of initialization. It is completely filled with air at this time, and it is at the time of temperature, so it will be initialization means the solution in initialization. So the whole microchannel is at the temperature 293 with no water in this, only air is present at this time. We click on the initialize, so it will initialize the solution for us. It is the initializing the solution, so it has done the initialization. So now from here, mark adapt, we select on the region. From region, I enter the value. I am doing this adaptation, this marking, because this whole section in which the water is going to be filled, water will start filling from here and it will come here. When it will come here, then the slug will be formed. To save our computational time, I will mark that the side channel is filled water from here inlet to this, so that we save our computation time. So I will enter the values for the x, which are 0.0192, 0.020. when you will study the geometry, you will study the dimension, you will be able to understand the values that I am entering, the data, the coordinates that I am entering here. So that I enter here, then I enter here the let me correct it. Then we click on the mark, then we click on the patch. I am doing this patching to save our computational time. I click on the water, set the volume fraction to be 1, click on this registers to patch, then click on the patch. So now let me show you the effect of the patching. Change it to the temperature phases. Here the water, let it to be filled and save display. It will take a time, so now let me show you how had we initialized the solution. We had initialized that the whole microchannel is filled with air, there is no water. And after that, in initialization, I made sure that the water has been filled from here to the point here, so that we don't have to do computation for this whole length. If we had not done this patching, the water would start entering from here, and it will take many large time to come here and then start interacting with there, and then the water slug will be generated. To save our computational time, to save our energy, to save our resources, to save our computation time, I have patched this section to be water filled, so that we don't have to spend time on the computation of this section. So this is why the patching has been done here. So we can see that the water fraction of 1 red color water fraction is present from here, water inlet to this point. So now the computation would be done only for this section, and then it will start interacting with the air, and then the slug will start generating, and less time will be consumed in this scenario. And after this, we come to the run calculation. In this, we select the time step size. I will take the value of very small value -6 to be on the safe side to ensure the stability. In case of small time steps, we will have the solution ready for us in shorter time, but it may get unstable. And in the case of small time steps, it will take a large time for the solution to be made available to us, but the solution will be stable. It means simulation will not break down in the process. we select the time steps to be 7 lakh, or you can select any other value as per your requirement. Select the maximum iteration per time step to be 50 and select the voting interval to be 10. Then we go to the data file quantities. In the data file quantities, we will select the quantities that we want to be computed. So I will select all the variable, all the quantities, so that we are able to have all the quantities available in the post processing section, so that we can play with any quantity. It is taking time. It will take 1 or 2 seconds more for it to be open. So here are the data file quantities. I will select on all the additional quantities as well, so that we have all the quantities in our arsenal and we can use it at any time. We click on the OK. There is not much difference in the computational time if we select or not select these quantities. So it is better to have all the quantities available, so that in the further section in the post processing we may not feel that we should have selected that quantity, or we have not selected, so therefore we are not able to compute that analysis. So we have selected all the quantities so that we are able to calculate all the other parameters that we want to be calculated, or carry out any other analysis that we wish to carry out. After doing that, we click on the calculate, and now the simulation will start running. So simulation is getting ready to be proceeded. Now it has started. It is now calculating the solution. So we can see that cache and dat files are being written in the destination folder where the files are going to be saved. Actually my PC is a bit slow, so it is taking time, otherwise it should not have taken that much time. So you people would have to bear with me for a little more while. It is actually taking some time. You would have to wait. Now the dat file is being written. So I have told you the whole procedure in which way we will construct the geometry. We have discussed the meshing. We have discussed all the simulation settings, which pressure discretization scheme, which time formulation scheme, how the boundary layers are set up, how the properties are being defined, how the patching is done, and how the time step size and all other various parameters have been selected and are used. So how the initialization is done, how the files are saved, how the contours are shown. So in this way the whole simulation is being done, and has been done for my MS thesis project. So as we can see that the time step size is minus 7 or minus 6, and the number of time steps is in the lakhs. So it will take not just hours, it will take many days, 3 or 4 days for the simulation to be completed. So I am not going to into those details. You can carry out the simulation by your own self by following the procedure that I have described in this tutorial. First make the geometry, then done the meshing, and then come to the simulation setting and set all the simulation that I have described here, and then set all the parameters that I have described here, and then you will have your results and your simulation to be running. So that is all from my side. Thank you very much.